Hi, I'm Amy. Let's make some common sense out of the factoring technique of evaluating limits. When you're solving limits, the first thing you always want to try is direct substitution. Sometimes that'll get you a numeric value, which means you found your limit. Sometimes you'll find that you get infinity or the limit does not exist. And sometimes you might get 0 over 0, which is an indeterminate. So for example, on this particular problem I have here, it says the limit as x is approaching 3, and here's the function, x squared minus 9 over x minus 3. Now, something really particular happens as x approaches 3, right? Here, when we plug in 3, we're trying our direct substitution. We get 3 squared minus 9 in the numerator, and we get 3 minus 3 in the denominator. And hopefully you recognize that that top goes to 0 and that bottom goes to 0. So we got 0 over 0, an indeterminate. And just like indeterminate sounds, this basically tells us nothing, right? This tells us nothing. We could have a numeric limit, or we could have a limit that does not exist. We don't know yet, so we have to take further steps. So let's try factoring in order to simplify this expression. So again, limit as x approaches 3. Here's the function. I'm going to write limit again because I'm not going to plug anything in, so I'm still kind of evaluating the limit. So limit as x approaches 3. Now I'm going to factor the numerator, which as a difference of squares factors to x plus 3 times x minus 3. And of course our denominator was x minus 3. And what you'll see here is we have x minus 3 over x minus 3, which is equivalent to 1. So in effect, this limit is equivalent to the limit as x approaches 3 of x plus 3. We don't have that pesky denominator going to 0 anymore. Now we can try our direct substitution, plug 3 in for x, and we get 3 plus 3, which of course is 6. Our limit for this particular problem is 6. We know that x equals 3 makes the denominator go to 0. So we know that that function is then undefined at x equals 3. But since that denominator cancels away, we then know that since we do have a limit there, and the limit is 6, we know that we have a hole there. And I will show you what I mean by that. So 3 on the graph is right here. And what we're looking for the limit is as x gets closer and closer to 3 from each side, where is the graph heading? Since our graph is undefined at x equals 3, we can't have a point there, which is why there's a hole right there. But the rest of the graph is a linear function. And notice when we did that limit earlier, we simplified after reducing, we had x plus 3. That's a linear function. Y equals x plus 3 is a straight line with a slope of 1 and a y-intercept at 3. So the graph looks like x plus 3, but because it's written in a slightly more complicated form, that throws that hole into play as well. So x is undefined at 3. So where's the graph heading? From either side, we're heading towards that hole there, which happens to be at y equals 6. So as x gets closer and closer to 3 from each side, the f of x, the output value, gets closer and closer to 6. It doesn't matter that there is a hole there. The point does not have to exist for the limit to exist. So to recap, the first thing you always want to do on a limits problem is try direct substitution. If you get a numeric value, you've found your limit. If you get infinity, that limit does not exist. And if you get 0 over 0, which tells you nothing, you need to try something else. We tried what's usually the first thing you should try, which is factoring. And we found that by factoring and reducing, we were able to come up with a numeric limit. So the limit does exist. If we got infinity, that limit would not exist. And if we got another 0 over 0, well, we'd have to try a more advanced limits technique. I have a limits flowchart and other videos to walk you through those other techniques. So that's really the basics of this limits problem. I threw the graph in just for extra information to help you visualize it. Now for the rest of the video, if you want to stick around, I'm going to take a deeper dive looking at the limits from the left and from the right. If you're asked to find, for instance, the limit from the left, which is notated by x coming into 3 with a little minus sign, which means we're coming in from the left-hand side, you can try plugging 3 in yet again and figure out, okay, I get 0 over 0. You can then, okay, I'm going to rewrite the limit, 3 minus, and we factor, we reduce, and of course, we know that that's equivalent to x plus 3. I'm not going to go through the factoring a second time. This time now, if we plug in a value really close to 3, just below 3, 2.9999999, something like that, we're going to get a value like 5.99999, something really close to 6. So in fact, this limit, when you do plug in 3, you get 6. And again, visually, when you look at that graph coming in from the left-hand side, where are we heading? We're heading towards that hole at y equals 6. And likewise, for the limit from the right, that's signified with 3 with the little plus sign there. Again, by factoring and reducing, 3 plus, we would end up with an equivalent limit of x plus 3. We plug in a value just slightly above 3 plus 3, and of course we get something slightly above 6, which indicates to us if you plug in exactly 3, we know that our limit here is 6. And we'll look at the graph one more time. Yes, we're coming in from the right-hand side, also approaching y equals 6. Since both of these values, the left and the right, are 6, then we know that the two-sided limit does exist, and that is also 6. Remember, a limit exists if the limit from the left and the limit from the right approach the same numeric value. Has to be numeric, can't be infinity, has to be an actual real number. So this here is the two-sided limit, and that exists if and only if the left-hand side and the right-hand side limits are equivalent and, of course, equal to an actual number. If, of course, is if and only if. That means if the two-sided limit exists, then the left and the right-hand sides have to be equal. And if the left and right-hand sides are equal, then the two-sided limit must exist.